In this section, we're going to look at power series. A power series is a series of the form the sum from 0 to infinity of Cn times x to the n, where the x is a variable, its value is not specified, and the ci's are constants, and they're called the coefficients of the series. So this is like an infinite polynomial, and its value, if it exists, varies as x varies. So we already know a lot about the power series, the sum from 0 to infinity of x to the n. When you expand that, it becomes 1 plus x squared plus x cubed, etc., etc. It's an infinite polynomial which goes on forever, and each term is just 1 times x to the n. And if I were to set a particular value of x, say set x equal to 0, then the power series becomes the sum of 0 to the n. We assume for power series that 0 to the 0 is 1. So this is equal to 1 plus 0, etc., etc. And that infinite sum converges to 1. If I were to set x equal to 1 over 4 here, then this power series becomes the sum from 0 to infinity of 1 over 4 to the n. And again, that's a series I know a lot about. It's a geometric series with r equals 1 over 4. And it converges because the absolute value of r is less than 1. And in fact, I can also write down the sum. It's 1 over 1 minus 1 over 4, which is 4 over 3. If I were to set the x value equal to 2 in this power series, then for that specific value of x, the power series becomes the sum from 0 to infinity of 2 to the n. And it's 1 plus 2 cubed, etc., etc. And this series diverges. It's a geometric series with r equals 2, which is bigger than 1. Or you can see, obviously, that the limit as n goes to infinity of 2 to the n is not 0, so it diverges by the divergence test. The first thing we know is that a power series can converge for some values of x and diverge for others. Now, if you're thinking about this power series as an infinite polynomial, then the values of x where the series converges is going to be the domain of this infinite polynomial function, and where it diverges, those x values are not going to be in the domain of this infinite polynomial function. So these power series look like infinite polynomials, but there's one big difference. A polynomial, which is a finite sum of this form, its domain is all values of x, whereas a power series may have a restricted domain. In the case of the power series we've just been looking at, the sum from 0 to infinity of x to the n, we know from our knowledge of geometric series that this converges for values of x where the absolute value of x is less than 1, and it diverges for values of x where the absolute value of x is greater than or equal to 1. And we know all of that from our knowledge of geometric series if we just substitute our previous analysis with x equal to r. Let's have a look at this power series, or its graph, on Mathematica. So looking at the series from the sum from 0 to infinity of x to the n, it's a power series, and for any given value of x, it's a geometric series. So we know that it converges when the absolute value of x is less than 1, and it diverges when the absolute value of x is greater than or equal to 1. In fact, we can tell what the sum of this series is for x between minus 1 and 1. It's 1 over 1 minus x. Now, remember that a series converges if and only if the partial sums have a limit. And if we take the partial sums of this series as a global series, we get functions of x which are polynomials. The first partial sum the sum from 0 to 1 of x to the n is 1 plus x, and the next one is 1 plus x squared, it's a quadratic. The next one is 1 plus x squared plus x cubed, etc., etc. Here we're going to plot the graphs of these polynomials, 1 plus x squared, etc., etc., up as far as x to the m. Or, in other words, in summation notation, the sum from 0 to m of x to the power of k. Here we've taken m running from 1 to 20, and when I run the animation, you can see that for values of x between -1 and 1, the points on the graphs, the partial sums, have a limiting value, whereas outside that interval, they tend not to have any point where they settle, so the graphs don't have a limiting value. And remember, for this particular series, we can actually write down the sum. So for x between 0 and 1, if we look at the function 1 over 1 minus x, then the limit as m goes to infinity of 1 plus x squared, etc., etc., plus x to the m should give us the sum of our series, which is 1 over 1 minus x. So the points on the graph of these partial sum polynomials should tend towards the graph of 1 over 1 minus x as x goes to infinity for x between -1 and 1. So here we've drawn the graph of 1 over 1 minus x in red, and you can see it has a vertical asymptote, which is a point of discontinuity at x equals 1. And we're drawing the graphs of the partial sums of our series, 1 plus x squared, etc., etc. In particular, the sum from 0 to m of x to the k. As the values of m vary, the graphs of these polynomials are shown in blue, and you will see that as m tends to infinity, as the size of this polynomial gets larger, the graph of the polynomial gets closer and closer to the graph of 1 over 1 minus x for values of x between -1 and 1. Outside that interval, the polynomials don't have a limiting value, and they don't get closer to the function 1 over 1 minus x.